Hello and welcome to another problem solving session with Special Maths Academy. And in today's video, we are going to be covering the 18th problem from the Senior First Round Mathematics Olympiad 2020. And the problem goes like this. How many rearrangements of A, B, C, D, E are there such that no two adjacent letters are also adjacent letters in the alphabet? For example, A, B, B, A, C, D, E, they are not allowed. So for example, now these rearrangements A, C, D, and BE is not going to be valid. Why? Because we have we have like two adjacent letters here. It doesn't really matter which comes first or which whether C comes before D or D comes before C. They are adjacent, so it's not going to be a valid rearrangement. But a rearrangement like this, EC ADB, is going to be a valid rearrangement because A is not adjacent to B, B is not adjacent to C is not adjacent to D, and D is not adjacent to E. So this is a valid rearrangement, and this is not a valid rearrangement. So I just want to like clear up the example. The way I'm going to approach this question now is I'm going to like break it down to 5 cases. But yeah, because each of those cases like I'm going to be when each case is going to be like denote what letter starts that configuration, that rearrangement. So the first case will be like when A starts the rearrangement that is valid, that satisfies all the properties here. The next case will be when B starts, and so on and so forth. So now, but if we can be able to observe something that okay, so the 5 cases, let me just write down case 1. When A is the first letter, then case 2, out of 10 to repeat, when B is case 3, okay, there's actually no point of writing down. But what I just want us to observe is that counting each of those 5 cases, like I'm doing them individually and all that, is going to like take a longer time. So I try to like find a way to like shorten our steps or the counting that we may need to do. So I observed that the number of times, like the number of configurations that starts with A is going to be equal to the number of configurations that starts with A. Like I found a bijection between these two countings, and I'll show the bijection down later. That starts with A. And similarly, the number of configurations that starts with B is going to be equal to the number of rearrangements. Let me call it rearrangement, not configuration. It's going to be equal to the number of rearrangements that starts with what? D. So what how was I able to like find the bijection that works? So the bijection that worked was let's just denote it as this. Okay, let me just write any random rearrangement. Let's say AC. Let me write one that works. B D A C E. So if you notice, this is a valid rearrangement that works. So the bijection I found out was like if we swap A, anywhere we see A, we swap it to E, or we replace it with E. Anywhere we see B, we replace it with D. Anywhere we see C, we leave it the same. So C is like the identity in this mapping. Anywhere we see D, swap to B. Anywhere we see E, we change it to A. So like if you have with these 5 rules of the mapping or the function, we're able to get like if a configuration works and we apply this function to that configuration, then the new rearrangement or configuration is also going to work. So let's just apply this function to this rearrangement. So what we get, B maps to D, remember. So the new one will be D, B, E, C, A. And we also notice that this works. So I'll just leave it to the viewer to like try and actually show that it's a bijection. So like the way of doing that is like you don't like need to know all the rearrangements that start with E that work. You can just like say, suppose any rearrangement starts with E. Now try to like apply this function to it. I know like if it starts with E and you apply this function to it, to now start with A. So that's why I'm like saying the number of rearrangement that starts with A is equals to number that starts with E, and similarly, the number that starts with B is equals to number that starts with D. And also, like, make sure that if you notice, like, even as we apply this function, it still like satisfy these other properties here that no two adjacent letters are also adjacent letters of the alphabet. So like this mapping is still satisfied. It just doesn't like only swap the numbers. It still like satisfies everything. So I'll just leave it to the viewer to be able to like prove why this function here, this function I put in a box here, why it's actually a bijection. So you try to show that everything here is here, like everything that starts with A, you can find it's injective. You try to like show it's both injective and surjective, that everything from here you can go to this side, and from this side you can go to this side. Because you can also find the inverse of this function. It's not so difficult. So that being said, now remember, as I said earlier on, we have 5 cases. So, but now that we have found that number of rearrangement that starts with A is equals to number of rearrangement that starts with E, and similarly, number of rearrangement that starts with B is equals to number of rearrangement that starts with D, we can now reduce number of cases here to 3. So just like count number of rearrangement that starts with A, the one that starts with B, and the one that starts with C. So why if we are now able to find like this number and this number, our total number of rearrangements will be what? 2 times this plus this, like this plus this, 2 times the sum of the first 2 plus C. Because like there are an odd number of letters here, so like it can't really match up. Like I could have written a number of rearrangement that starts with C is equals number of rearrangement that starts with C, but that is trivial. Like it's not really special, so that's why I didn't write that part. So just have to like find number of rearrangements that starts with A and starts with B and starts with C. Then for these first 2, we add them up, multiply by 2 and add to C, and that will be like total number of rearrangements. So let's go now. Okay. So case 1. So I'll start with when the rearrangement starts with C. When rearrangement is still going to be cumbersome, but at least we are able to like reduce it to almost have the level of cases we have to check. When the rearrangement starts with C. Box is 1, 2, 3, 4, 5. So when it starts with C, C is the first one now. So how many are left now? So we are left with A, B, B and E. So yeah, we have to like just start observing things carefully now. So now if you look at these 4 letters left now, none of them has 2 adjacent letters to it. For example, E has only 1 adjacent left, that is D. D has only 1 adjacent left, that is E. B has only 1 adjacent left, that is A. And A has only 1 adjacent left here, that is B. So what we have to do now is to notice that since C starts this rearrangement, the next letter after it can neither be B or C, can either be B or D. Why? Because B and D are both adjacent to C, and we don't want that. So it means that the letter here is either A or E. So now we can break this to 2 cases, or actually we can still apply this as function here to these last 4 letters here, and we now like see that the number of rearrangement that starts with CA is going to be equal to the number of rearrangement that starts with CE. By applying the same function here, it's going to also be a bijection. So that being said, we can just find the number of rearrangement that starts with CA. Then after I'll do that, to find number of rearrangement that starts with C, we just multiply by 2. So we find number of rearrangement that starts with CA. So this is A. So now A is out of the way. So we have what? B, D, and E. So what do we do next? So what we're going to do next is now to notice that this question will have to like just be very, very observant here, because it's really necessary to solve this. So what we have to notice that D and E are adjacent. Like we are left with B, D, and E now. D and E are adjacent. B has no adjacent letter to it. So because of the fact that D and E are adjacent, it means that that D and E cannot both occur like at consecutive blocks of numbers, of consecutive boxes here. So it means that D and E cannot. Um, so it's not so difficult to like see that for that to be true, that B has to be this middle term here out of this last three. Why? Because if B is not here, if B is either at one of these corners, then we have two consecutive boxes that are free, and D and E have to occupy that. But D and E are consecutive, are adjacent, so that will not be like part of what we are meant to count. So that's why B must be this middle one among these three last empty boxes. So B is this middle box here. That's like the of this last three. That's like the fourth box of the whole arrangement. So if B is now here, it means that E can either be here. It means that we can conclude with ED or can conclude with DE. So just like have to check these two manually whether they give us any invalid rearrangement. But it's not so difficult to like see that both of these arrangements will work because neither of them has consecutive adjacent letters to each other. So it means that in the case like when the rearrangement starts with CA, we have what two ways. There are like two possible rearrangements that satisfy the question. Then remember I say that the number of rearrangement that starts with CA is going to be the same as number of rearrangement that starts with CE because of this bijection, like I explained earlier on. So it also means that the number of rearrangements that starts with CE, because this second box can either be C or E. So number of rearrangements that starts with CE also be 2. So it means that total number of rearrangements that starts with C will be what? 2 plus 2. That will be what? 4 rearrangements starts with C. So we're done for this first case now. So now to go to the case 2. Find number of rearrangements that starts with what? B. Number of rearrangements that starts with B. So we'll just draw 5 boxes also. Let me use a different color now. 1, 2, 3, 4, 5. So it starts with B. Scroll down now. You just have to very observant. Now that I start with B, what are the alphabets that are left? A, C, D, and E. So remember, since it starts with B, this next letter after B can neither be C or A. So it's either D or E. So if this letter here is D, so now we break it to subcase 1 now. This one we can't really apply the bijection here. So that's why we like actually count the two of them differently. So we break it to subcase 1. When it starts with B, when the next one is E. Then subcase 2 will be when it starts with B and then the second letter is D. So we're now left with the last 3 boxes here. So what is this? What letters are still vacant? A, C, and D. So observing this now, as we did in the earlier case, C and D are both consecutive. So because of the fact that C and D are both consecutive, we must have that A should be here. Why? Because if A is not here, we have 2 consecutive blocks and C and D have to occupy it, but to now break the last condition that we don't want adjacent alphabet. So A has to be here. So after A is here now, we're left with 2 possible configurations. That is either C is here, D is here, or D is here and C is here. So we notice that this first configuration here, B, E, C, A, D, is valid. Like it doesn't break any of the conditions of the question. But this second one, B, E, D, A, C, is invalid. Why? Because C and D are adjacent. So this is invalid. So it means that in this subcase, we have only 1. We don't have 2, we have only 1. So subcase 2. It's really cumbersome, but we should just like try and make sure we don't count something twice and we don't miss out anything. So this is when the first 2 letters are B and D. Because remember, we showed earlier on that the second box has to either be E or D. Because it can either be A or C, because A and C are both adjacent to B. So what are we left with here now? We're left with A, C, and E. So um so now if you look at this next box here, now this is D. This box here now, on the right side of D, it can neither be E. Why? Because E and D are adjacent, and it can also neither be C. Why? Because C and D are adjacent. So what does it mean? It means that it must be A. So A is out of the way now. So we're now left with these last two, C and E. So just like check two of them manually and check if they work. CE or EC. So BA, these first ones are all good. So now let's just check whether we have any consecutive adjacent alphabets here. And we see that we don't have. This is good, this is good. So in this subcase 2, we have what? 2 ways. So it means that total number of so now in the whole general case now of case 2, not case 1, sorry, of case 2, total number of rearrangements was 1 plus 2. So that's what? 3 ways. There are 3 ways here. They are now left with the last one, case 3. Case 3. Case start. So let me just use different letters now. 1, 2, 3, 4, 5. So A start. So this is A. Then we're left with what? B, C, D, E. So what can we now observe from here? So we can observe that letters C and D here, like out of the 4 letters that we haven't yet chosen, okay, we have that they both have two possible adjacent letters that haven't been chosen yet. For example, C has B and D here, it hasn't yet been chosen, and D has C and E. So what I'm trying to like show is that these two middle terms, these two middle boxes here that have a box to its left and to its right that haven't yet been occupied, neither C or D can occupy any of these boxes here. So why? Let's say suppose C occupied one of these boxes here. It will mean that we should have a letter here that should not be adjacent to C, and also another letter here that should not be adjacent to C. So but now, okay, let's say C occupies this now. So if C occupies this, what are we left? So I'm left with B, D, E. So but out of these 3 letters here, 2 of them are adjacent to C. That is D and B. And we're looking for 2 non-adjacent letters to C because C occupies here, but there's only 1 non-adjacent letter to C. So like it's not possible to like fill these 2 slots. So that's why C should neither be one of these 2 middle terms, 2 middle boxes out of these last 4. And similarly, D should neither be one of these 2 middle boxes in the last 4. Because both of them have adjacent neighbors, 2 adjacent neighbors are still here. So for that reason, it means that C and D should occupy this and this. So either C is here, D is here, or D is here, C is here. And that implies that B or E should occupy this and this. So either B is here, E is here, or E is here, B is here. So what I'm now going to do is we're just going to like break it down to subcases also. Yeah, there are a lot of subcases, but yeah, thankfully we're able to handle all of them. So subcase 1. When we start with AC. Then remember, as I said earlier on, D can neither be this middle one, so D has to be here. So when we have this now, we're left with either these 2 completions, EB or BE. But we see that ACEBD is a good one. It works well. It works out well because none of them are consecutive. But ACBED has a problem. Why? Because C and B will be consecutive here, adjacent. So this doesn't work out properly. So it means in this subcase we have what? We have only 1 way. So now subcase 2. When we start with what? A and D. So that is A, 3. So when we have A and D, and remember, since C can neither be this or this, C has to be here. And we actually now check these last 2 ones also. And we see that this is consecutive, so this gives us a problem. But A, okay, I wrote the same thing twice. Okay, no wonder. This is BE. For AD, BEC is all good. We don't have any consecutive any adjacent letters together. So this one works out properly. So it means this gives us one way also. So it means that total number of ways in this whole case, 3 is what? 2 ways. So let's go down now. I'm almost done with the question. So if you scroll up, let's scroll up and see what we have. Remember in our case 1, we had that when the rearrangement starts with C, we had 4 ways, 4 possible rearrangements. When it started with B, we had 3 possible rearrangements, and when it started with A, we had 2 possible rearrangements. So start with A, 2 ways. Start with B, 3 ways. With C, 4 ways. Then because of the bijection I explained on at the beginning of the video, if it starts with D, it's going to have the same number of rearrangements as it starts with B. So that will also be 3 ways. And if it starts with E, it's going to have the same number of rearrangements as it is when it starts with E, when it starts with A. So that will be 2 ways. So the total number of ways will be 2 plus 3 plus 4 plus 3 plus 2. That is 14 ways. So the answer to this question is 14. That gives us our option C. The answer to this question is C, 14 ways. So as you can see, like all starting like trying to like find the number of ways of counting by what the first letter is. It helped us to be able to break this question down to multiple cases, but we're able to handle all the cases, and the bijection helped us like reduce the number of cases to half, or almost half. So those two ideas helped to save some time while we encountered this. And I leave it to the viewers to be able to like maybe write out all the 14 possible configurations or possible rearrangements of this, maybe in the comment section. But also, a way of solving this question, you can actually like go like the most brutal way and try to write out all the 5 factorial ways, that is 120 ways of arranging A, B, C, D. Then look at them individually and check which of, out of these 120 ways, like look at them individually and check which of them satisfies it. It's going to be long and order, but if you can be able to like be very careful and looking at them, you also be able to get the answer. And it requires less rigor or less creativity. So it's also good, especially when you're like desperate in the exam hall. So that was the other way I solved it. I tried to solve it in those 2 ways, but this one was more presentable. That's why I wrote this one down. So that's all I have for today, and I'll see you some other time. Thanks for watching.